Databases store the most valuable assets of modern systems: user credentials, financial data, health records, or even internal company secrets. A breach doesn't just hurt your users. It can ruin your company, your reputation, and your legal standing. So how do we keep this information safe in your database? Broadly speaking, we rely on two lines of defense: access control that governs who can interact with the data, and encryption that protects what the data looks like if someone does access it. Access control decides who can use your data. Encryption decides whether anyone can understand it. Miss either one, your database will become a toast. In this video, we'll unpack these two pillars of database security: access control and encryption, and show you how they work together to protect sensitive data from misuse, leaks, and attacks. Let's start with access control. Access control governs who can do what in a database. It prevents unauthorized users from reading, modifying, or deleting data. There are three types of access control that you should be aware of, including discretionary control, mandatory access control, and role-based access control. Discretionary access control is the simplest one, but it only works for a small application or toy project because it doesn't scale very well. This type of access control is about the database admin manually determining who can access the database and what permissions they have. So there's not much to say about it. In contrast, the two other types of access control deserve some good explanation. Mandatory access control is about assigning a hierarchical levels of clearance to databases, tables, columns, or even rows. And at the same time, it will assign the same hierarchical levels of clearance to its users. A user can only access some data if his or her assigned clearance level matches or exceeds that of the corresponding data. For example, think that we are running a database of a higher education institution and it defines three clearance levels: public, sensitive, and confidential. We then assign them to different tables in the database. Tables like student and course are assigned the public clearance level, grade is classified as sensitive, and medical is classified as confidential. We would also assign such clearance levels to different users who need to access the database. Only when one's clearance level is the same or higher than the corresponding table, the user can access its data. In short, mandatory access control is about managing and assigning a hierarchical of clearance levels to both users and tables. Mandatory access control is mostly used in government, military, and other high-security environments where protecting classified information is critical. In comparison, role-based access control is about assigning access permissions to roles rather than each individuals. Users are then assigned roles based on their job functions. This simplifies the management by grouping permissions into roles that reflect organization structures. For example, think about that we are running a database for another higher education institution and we define three roles, including student, teacher, and admin. We then associate the access permissions to each of the roles, like this. After that, we can assign the roles to different users who need to access the database, like this. As you can see, sometimes a single user can be assigned to multiple different roles. Role-based access control is used almost everywhere outside of a strict military or government settings, especially in business, education, healthcare, and online platforms, because it's much easier to manage the mandatory access control and scales very well in comparison to the discretionary access control. When you use SQL to achieve role-based access control, the syntax varies from one database to another. So here, we will only show you an example in which there's some baseline consistency. After all, SQL standards do define a few of the clauses that are key to access control. Think about an online store named the Sci-Fi Collective. In its database, we need to define 3 roles: users, analysts, and administrators. By users, I mean the ones who are the customers of the Sci-Fi Collective and who shop online. The users have read and write access to a few tables, but they can't delete or update anything. The SQL code of creating the user role may look like this for MySQL or MariaDB. It starts by creating the role using the createRole clause, followed by the name of the role, up to your choice. After that, we grant different access permissions to this role, such as the permissions to view data, insert new data into different tables. Dot notation is used here to concat the database name and the table name. As you can see, the grant to clause is used to achieve this goal. Select means view permissions. Select on Sci-Fi Collective. .product means the view permission on the product table. Insert means the permission to add data. Insert on database name. .purchase means the permission to add data into the purchase table. After these 2 steps, the role of users is created. Whenever you have a new user who should have this role, you will grant it to that user. For the admin role, you will follow the same 3 steps to create the role first, then grant different permissions on different tables to this role. In the end, when you have a new user who should have this role, you will assign the admin role to him or her. One thing worth noting here is that you can combine multiple permissions, such as viewing, adding new data, updating, or deleting data of the same table to this role, and pack them into a single grant to clause. The different permissions are separated using commas. That's everything about access control. Let's move to discuss encryption now. Encryption is about protecting data by converting it into a coded format. So if the data is stolen, it can't be read in plain text at all. The 2 most commonly used encryption approaches include one-way encryption and symmetric encryption. We will look at the 2 types of encryptions one after another, starting with the one-way encryption. One-way encryption, also known as hashing, is a cryptographic process where data is transformed into a fixed size string of characters, which is typically a hash value or hash code. The key characteristic of one-way encryption is that it's designed to be one-way function. It's easy to compute the hash value from the input data, but extremely difficult, or say practically impossible, to reverse the process and obtain the original input data from the hash value. This makes it useful for scenarios where you need to verify data without storing the original data in a readable format. Some of the popular one-way encryption algorithms include decrypt, PDK-DF2, and SHA-512. To enhance security, a unique salt value, or say a randomly generated string, is often added to each password before hashing. This prevents the attackers from using pre-computed hash tables to crack passwords. Regardless of the varying password lengths, the hashed results always have the same length as some binary data. It's a common and recommended practice to actually encode the hashed byte data into strings and store them using char in your database. Encoded hashes can be printed, logged, copied, and debugged more easily. Plus, encoded strings are safe to include in URLs or JSON because the raw binary data may include null values, controlled characters, or invalid encoding sequences. Let's see an example where one-way encryption is applied and explore its implications for database design. Think about the database of the same online store, the Sci-Fi Collective again. In your first iteration of database design, you developed a table named user to store all the information of the customers. There's a column named password that currently stores passwords without any encryption. Now, with the newly acquired knowledge on encryption, you decide to use decrypt as a one-way encryption algorithm to encrypt the passwords. Decrypt generates salt internally and results in a 23-byte binary data after hashing. When you convert the binary data to strings using base 64 encoding, all hashed passwords will be 60 characters long. Since salts are unique to each password, you do need to store them, but decrypt handles that as well. So all you need to do is to make sure that the password column has enough space to store the strings in the hashed format. Like this. As you can see, the change introduced to the database design is very small, yet critical. It relies on your understanding that passwords cannot be stored in plain text, which encryption algorithms to use, and how that algorithm handles things in its own way. If a different encryption algorithm is used, things could be slightly different. For example, if you decide to use SHA-512 to handle the one-way encryption, things will be slightly different. This encryption algorithm doesn't generate salt internally, but still requires salt for hashing. When passwords of different lengths are hashed using this algorithm, they all end up as 64-byte binary data. When such data is encoded using base 64 as strings, they will all be 88 characters long. Remember, SHA-512 still requires salt for hashing. So the backend server needs to generate salt, use it to encrypt the passwords before ever storing them into databases. Beyond that, since salts are unique to each hashed passwords, you do need to store them just in case you need to repeat the same process in the future for the same given password. You can choose to prepare a separate column named password salt to store the salt as binary data. Or you can follow the lead of decrypt and concata salt with its corresponding hashed password as a single piece of data, and then encode it as a string. This decision may not be all yours to make because it requires the backend server to cooperate. Regardlessly, such a decision will impact the design of the user table. Now, let's move to talk about the symmetric encryption. Symmetric encryption is like having a single key that both locks and unlocks a box. You use the same secret key to encrypt data when you need to store it into the database, and you use the same key to decrypt the data when you need to read it back. This is different from one-way encryption, or say hashing, where data is scrambled but can never be unscrambled. In contrast, symmetric encryption is reversible, meaning that you can always get your original data back if you have the key, making it ideal for storing sensitive information that you need to retrieve later, like credit card numbers or personal details. Common symmetric encryption algorithms include Advanced Encryption Standard, Triple DES, and Blowfish. Each algorithm has a set of variants. Depending on the key lengths, such as 128 bits or 256 bits, AES has three variants: AES 128, 192, and 256. The key length determines the level of security and the computation power that's required for encryption and decryption. The longer the key is, the higher the security and the computational requirements are. Let's use AES 256 as an example of symmetric encryption and think about its application to the same database that we just visited. As you can imagine, the database needs to store the payment information from its customers. The table for this task is named payment method. When a customer or the user buys anything and takes the option to save the payment information for future use, this table stores the credit card information accordingly, including the card number and expiration date. As it stands now, neither of the two columns are encrypted. In case if you wonder, okay, we are storing the credit card numbers, the expiration date, but why don't we store the CVC numbers too? It's all about following the payment card industry data security standards, which recommends not to store the CVC numbers at all. After all, CVC number is either requested again from users or not necessary when the card is used again for future transaction. Assuming that the first transaction, of course, went through successfully. Based on this standard, card numbers and expiration date can be stored in your own database, but both need to be encrypted. As you know, a card number is 16 characters long and expiration date is 4 characters long if you skip the slash that separates the month and year numbers. As it stands now, the table fails to encrypt either of the two columns considering their data sizes. If we use AES 256 to encrypt both columns, we need to get on the same page in terms of how AES works first. These algorithms use a 256-bit secret key for encryption and decryption. It operates on blocks of 16 bytes of data. If the input data is not a multiple of 16 bytes, one block will require some padding so that you always have a set of 16-byte blocks. Beyond that, AES uses a 16-byte initialization vector to strengthen encryption. Although the initialization vector is not a secret, it has to be unique per encryption. For example, think about how an expiration date August 2029 is encrypted using AES 256. First, the 4 characters, 0829, need to be padded and encoded as a set of 16-byte blocks of data. After that, it is concatenated with the initialization vector. In the end, the combined string will be encrypted using AES algorithm and encoded as a string. This process will turn both a 16-character long card number and a 4-character long expiration date into 64 characters. In other words, if you intend to encrypt both the card numbers and the expiration dates, you need to increase the data sizes of the two corresponding columns to 64 characters. In addition to that, you will need to store the initialization vectors for both the card numbers and expiration dates, because an initialization vector is unique per encryption. If you were to store the initialization vector separately from the encrypted data, you will need 2 more separate columns that store binary data of 16 bytes. It's typically unnecessary to encode the initialization vectors as strings, so binary data will do. If you don't like this option, you may choose to encode the initialization vectors as strings and concat them to the encrypted data, for example, always at the beginning of the encrypted card numbers and at the beginning of encrypted expiration date. In such a case, the encrypted card number plus initialization vector will be 88 characters long. The same can be said for expiration date column. As you can see, encryption only leads to change as minor as increasing the data size of the target column in a database. But a lot of thinking and understanding goes behind the scene. You may also wonder if the secret that's used for encryption and decryption needs to be stored into the database as well. The answer is no, absolutely no. Each initialization vector is unique per encryption, so they need to be stored and mapped to each encrypted data. However, the key that's used for encryption and decryption remains the same all the time. So it is typically stored in key management services or hardware security modules. Regardlessly, You shouldn't store the key in the same database, because it makes a single point of compromise. If an attacker gains access to your database, they get both the encrypted credit card numbers and the key to decrypt them. This makes the encryption essentially worthless. It's like locking your front door but leaving the key under the doormat. In this video, we covered two different aspects of database security, including access control and encryption. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Cracking Relational Database Design, which dives deep into the database design using real-world examples to explain the concepts. You'll be able to find a link to the book in the first comment.